All right. Okay, so we can definitely start here. Perfect. Thanks, guys, for confirming audio and video were. All right. So now that these technical issues are actually solved, one more thing before we start. I hear myself on the audio. Okay, too much. Thank you. So now that these technical issues are solved, we can start. Thanks for attending this talk. I'm very happy to be here today at Live Embedded event, the second session. And today we're going to talk about boats, about marine, sensors, and the cloud, which is why I mentioned the talk is some kind of a data journey here. My name is Vincent Rubiolo. I'm one of the architects here at IoT.bzh, focusing on cloud and embedded Linux. I've been a Linux user for quite some time now, since about, I think, 2004. And in the previous lives, I've also worked with RTOSes, including VxWorks at Wind River, shell loaders, debugging tool, in both France and the United States, where I lived for 6 years. I was part of the hypervisor team and did work on certified systems as well. And more recently, I've been busy with deploying like front-end, back-end application cloud native over Kubernetes. And I've put 2 links if you need to reach me, my email address, my LinkedIn profile. Feel free to use that to drop me a note if you need, before, after, during the talk, as you see fit. I mentioned IoT.bzh. You might have listened to Julien's talk an hour earlier. He also introduced the company. We're located in Brittany. We're a team of about 30 people, and our lineage goes back to Wind River itself, actually, in the 1990s, to Intel, the Tizen project, more recently automotive-grade Linux. And more recently, we've been actually busy developing our product, which is named redpesk. And that's product, is a software factory, basically, allowing you to develop your applications on top of both a tailored embedded Linux distribution, as well as the cloud side of things, which we call the factory, that allows you to monitor the build and the quality of your packages that you might develop on top of all that distribution. And one particularity here is the long-term support we also focus on. We're talking 10 to 15 years here for the support of that distribution. And we'll see how this matters in the context of marine and boating. Now, what we're going to see during our talk is, first, we'll start with the business environment and the industrial requirement of the marine sector, things you might not be familiar with unless you actually work in these specific areas. So I'll start with that. Then we'll move on to the anatomy of a typical modern connected boat, what that means in terms of data connectivity, what that means in terms of link quality in particular. We'll follow on with some typical issues you might see in that particular sector, especially around marine cybersecurity. I'll then move on to introduce the project we're working on, which is Synatic, a smart boat project. And I'll devote the second part of the talk towards the vision and the architecture and also the implementation that we've selected and designed to ensure that data journey can be done from the edge up to the cloud. And we'll wrap up with the usual perspective and Q&A at the end of the talk. All right, so with respect to business requirements, now this market has definitely some specifics. You might be familiar if you work or in the auto sector of some particularly of that market too. Boating and marine has specific requirement in that regard. And I've put down 4 main points that I wanted to highlight here. So the first is the lifespan of the equipment. If you take a small or medium-sized leisure boat, the lifespan is around something like 10 years. And the higher and the bigger the ship you go with, the longer the lifespan. If you take the big cargo ship, for which I put a picture down at the bottom, we're talking more like a range of 20 to 25 years, actually. That's pretty common here. That can include an operation called a refit. If you're familiar with aeronautics, like planes, out of a certain period of time, they would get actually put to maintenance, completely disassembled, verified, parts upgraded. It's the same for these kind of vessels here. Another important point is that most ships are actually pretty unique. That's a pretty significant difference compared to cars. Unless it's a very small ship, it's almost made to or built to order. You wouldn't see a second identical ship made this way. One more point is that the shipyards are usually far smaller companies than the automakers. You might know the usual automakers, very big company, lots of capex. The shipyards are usually much smaller. And that means that contrary to the automakers who can invest and excuse me, invest and design custom toolings, the shipyards will try to use as many standard parts as possible. And finally, the costs are definitely not the same. If you were talking, they are much higher. If we talk about a leisure ship, medium size, it's usually around 100K, 100,000 euros. A cargo ship is more in the range of 20 to 25 million euros. And that actually drives the type of operations in terms of ship maker, ship owner, freighter, or charterer that operates the ship. We're gearing more toward things that relate to buildings. And we'll see how that is expressed in particular here. The industrial environment is also definitely not the same. I mentioned the lifetime here of a car. For an industrial or marine equipment, they will operate more like factories, 24/7. That's usually the goal. They would do that in very harsh and friendly hardware environments, like seawater, as every sailor knows. It touches an equipment, will start corroding it. The temperature variations can be very high, from cold to hot, vibrations and shocks. So the environment is very demanding here. And if you look at the picture of the engine room, the one at the top, or the alternators, the one at the bottom, you will see it actually looks more like a factory or a civil infrastructure platform than an actual boat. And the one of you following the CIP project, the Civil Infrastructure Project, know what I'm talking about here, especially in terms of lifespan, like the 20+ year support here. These, due to the requirements to operate in these harsh conditions 24/7, it's usually a matter of fact that the equipments are replicated so that the system is resilient to breakdown. If you look at the bottom picture, the alternators, it's very common to duplicate the engines, duplicate the alternators, and several critical parts of the ship would also be duplicated so that there is no single point of failure here. You do not want your vessel stranded in the middle of the ocean, and this is what this redundancy provides. And finally, one thing worth noting here is the shipyards, just like the automakers in this case, are excellent mechanical engineering company. And that's what they focus on primarily. They usually have little to no software expertise. Software is seen as a cost of doing business. And their primary focus is usually definitely mechanical engineering. So with these two slides, I wanted to give you more specifics about the environment. Now we can actually move on to what it means in terms of a boat, the data connectivity, right? I've put here a picture of a medium-sized leisure boat. Hopefully this is legible. You can see the network of equipment connected. It's already starts to be quite complex, integrating heterogeneous sensors and buses over different protocols. NMEA 2000 is very common, especially in the leisure business. But as you go toward more industrial ships, you see more industrial protocols like Modbus, or even older protocols like J1708. And I'll talk about that in the further slides, talking about CNATIC, which is actually a serial-based protocol like 9600 baud per second. This is more like what you find in industrial facilities. That's for the inside of the boat. With respect to the connectivity outside, that connectivity is multiple, right? It's often unreliable or random. You have Wi-Fi, only usable at port range, unreliable if you're in a marina, have lots of masts from the sailboats. It's crowded, doesn't work very well. 4G is definitely a lot better, especially if you have an onboard antenna. You can actually go as far as 30 miles from the shore. So this is a good connectivity. But if you're in the high sea, as say a cargo or a container ship can be, this is not sufficient. And in this case, you rely on satellite connection like SATCOM. And this way, you always actually have connectivity everywhere. But one thing which is important is, depending on where you're located, you will have a bandwidth that actually varies. And it can vary from, say, multiple megabytes. I put like 2 is typical, can go as far as, say, 4, to something like 150 kilobytes per second. And the other important thing is, it's actually can be very costly in terms of connectivity. The example I mentioned, the 150 kilobyte per second, it's usually over the Certus constellation, and we're talking $10 per megabyte of connection. And this means, I'm going over to the next slide, like slide 8, we need to be able to manage the data link quality and prioritize that data so that when the bandwidth is low, you only actually provide and transfer only the most important type of data. And you can see that on the right is a picture of a very nice animation from the Iridium. That's the Iridium satellite constellation. And you see those satellites permanently going around in low Earth orbit and covering the Earth here. With respect to the cloud connectivity of the boat, it goes 2 ways from the boat to the cloud. That's used for monitoring. The data is uploaded, position, fire, flooding alarm. For sailboats, you'd be interested in knowing whether you're drifting. And the connectivity also goes the other way, from the cloud itself to the boat. In this case, you would act upon equipments to do remote configurations or software upgrades in this case. And that means, in terms of requirements, you need to be able to actually do over-the-air updates and software updates. Being able to update critical parts of the connected boat over the air, that's something that's a requirement. And of course, given the redundancy requirements and operation you have, if anything goes wrong, the rollback needs to be for granted so that you do not interrupt the operation of the ship. Needs to be done also with identity and security taken into context. I'll talk about that more in the coming slides, but with respect to identity and security, there are 2 aspects to it. One is the static part. When the ship is built, the equipment would get access rights set, and that will not change throughout the course of the ship unless there is a refit. But there is another part which is dynamic. Multiple personas with different access rights, potentially revocable, need to be able to access the ship at different periods of time. We'll get to that in more detail. Finally, the cloud-side infrastructure has the usual scaling, load balancing needs, as well as a strong focus on security here. And talking about security, you've all heard that cybersecurity is a big topic and that the attacks on various kind of equipments have been definitely on the rise these past years, and in all sectors like IT with SolarWinds, for instance, industrial. I think it was 2 weeks ago, the Colonial pipeline on the east coast of the United States was crippled by a ransomware, and they basically stopped delivering fuels to multiple states of the US here. Cars are no different, of course. Jeep hack, the big Jeep Cherokee hack a few years ago, total remote control of the vehicle through the 4G access point that was embedded there. And healthcare is no different too. Multiple hospitals have unfortunately been crippled again by ransomware in this case. And the boats and maritime sector are really no different here. And that led organizations like the IMO, the International Maritime Organization, to issue standard mandating that cybersecurity be taken into account. And this has started to be enforced starting this year, with the advice from the IMO being that states stop delivering permits to boats for which there is no cybersecurity plan in the global ship risk document here. That's for ships. For ports, it's a little bit behind. I think it's more on the sovereign national side, right? Boats are at sea. It's a common place to regulate. And so there's no, as far as I know, standard for port cybersecurity, rather best practices documents. I've put two here. The one on the right is from the UK Department of Transport. The links are at the end of the presentation. Now, if you were talking about sample marine cyber attacks target here, a ship is very big, and so it's composed of different subsystems, which can be mapped to industrial subsystems too. The main target for attack would be the GPS positioning system. If you do that, you're able to run the vessel aground, potentially causing millions in damage. You can also make it drift into forbidden areas for which it's not licensed to go, potentially starting a diplomatic crisis. The mitigation around these kind of attacks, again, they involve usually redundancy. You would couple multiple GPS system with the IMU or multiple IMU, the inertial units, and couple that with ground positioning. You're able to mitigate these kind of attacks. Another kind of attack is through the AIS transponder. Every ship embeds an automatic identification system transponder that is broadcasting to other ships its position and characteristics, as well as to ground station. And the system runs over VHF, so you could technically pretty easily DDoS it. And in this case, if you're successful, there is no real mitigation strategy for the charterers or captains than falling back on radar, which has a much lower range, or even like visual contact, the old style way, which is not very, very efficient. That's another type of attack that you need to be aware of. Of course, the ship is a physical system, so the higher and deeper you can go on the ship in the system, the amount of attacks actually grows in this case. And that's why most best practice or security document will actually focus on securing the parts of the ship. That's it for the small focus I wanted to do on the cyber attack part. I now want to talk a little bit more about what I'm working on, and which is introduce you to SEANATIC, the smart boat example that we're working on. It's a first step towards the autonomous vessel. In that regard, we're gathering boat sensor data from multiple subsystems. We'll see that in the next slide. And we're feeding it into an AI for analysis. And the end goal is to provide insights into boat operations to either the ground or the captain and the boat users themselves. And the idea being that with that amount of data, like say, take an oil filter, for instance, if you're able to monitor the engine temperature, the life of the oil filter, and combine that with the scheduled preventive maintenance windows, you can optimize that with trained model on the AI on a given fleet of ships. And this way you can optimize maintenance and provide useful data to ship makers, ship owners, charterers, everybody that operates or builds the ship. It's a consortium between multiple parties and companies. Azimut is doing the UI part. We at IoT.bzh are focusing on delivering the OS and part of the data staging and collection. PRU is our ship maker. Thalos is handling all the SATCOM and communication. And the UBS University is doing the AI part. That's an ADEM project here. I didn't put the link, but we have a website as well, cynatic.bzh, which you can go to get more information on the project here. Technically speaking, I've put 2 pictures from the ship itself, where we were just a few weeks ago. Our demonstrator is the Almac. It's a 44-meter long ship, 10-meter wide. You can have about 25 people on board. And it's a training ship. It moors in Concarneau here in Brittany. And it's used to train sailors for merchant marine. In our project on the data collection side, what we're focusing on right now is the main engines. Remember, it's duplicated, so we have 2. They are associated diesel generators. Again, we have 2. And they use these industrial protocol like that I mentioned earlier, like J1708. And also part of the equipments are using NMEA2K. We can combine that with actual AI model, and the diesel generator actually has a pure software model too that is providing by the manufacturer of the generator, so we can simulate maintenance or problems on the generator. When we are doing actual data collection, we are connecting that to a Siemens PLC IO subsystem that is then connected to Modbus on our industrial gateway. And that's where the rest of the data staging takes place. Connection-wise, we have 4G, LTE, satellite, Wi-Fi, and we can actually load balance and do QoS over that. We'll see how that goes in the following slides here. Now, I wanted to mention and detail a bit the vision for the design that we have with respect to pulling the data here. What we've implemented here is basically we're taking the data out from the boat sensors, we're injecting them into a local Redis data store, and then we're selectively replicating that store, that cache, to the cloud. That's basically how it works. And that way we can bridge the edge and the cloud. And once we jumped on the cloud side, then we can funnel the data back into whatever's needed, be it an IoT hub like Azure, talk to MQTT brokers like the one that Amazon provides. And we're able to do that with end-to-end security through our application framework here. And I won't go over, I have set a slide here for the application framework. I won't dive too much into it. There is a lot of content. I've put the links at the end of the presentation. What it allows us to do is define multiple security contexts, load applications into them, and abstract away the communication between those applications. So an application is not aware of where another application it's talking to is actually located. It could be on the same board, it could be on a totally different board, and if you attended Julien's talk this morning, again, it could be where he talked about Zephyr and Linux communicating. It could actually be on a totally different hardware, on a microcontroller, as opposed to a fully fledged CPU. So the two important things to note here, location, abstraction, and security context. And we have a notion of binder and binding, the binder being the application loader, the binding being what runs inside. And I'm mentioning that because now I want to dive a little bit more into the architecture here. And this diagram, will go over it in the following slides. We have three main parts. The left is the edge, the right is the cloud, and in the middle, in green, is our cloud publication service that allows to bridge the two. And I'm going over several parts of this schema in the following slides. Now, if we start with the edge, remember I mentioned the binding service application. We have one which we call the signal composer, and it's able to pull data out of sensors from buses like CAN, Modbus, or various types of sensors. We can extend it through a plugin architecture, and we use it to fill in a Redis local data store through another binding, which is called the Redis binding. We use RedisTimeSeries, so we have all the time series extensions available. And that way we can put the data into Redis itself. And we also contributed back some changes to the Redis projects, namely the support of binary data that we're using and that others can find useful. It's currently undergoing the merge request on GitHub in the main project. That's it for the edge. The center part is the cloud publication. And we're using it as the nexus for data exchange. It reads from the local Redis store and writes to the remote side, right? And I just wanted to take a moment to actually mention how this is done. I mentioned earlier the binder that's able to, it's a process and it runs in a particular security context, and it loads shared libraries into these security contexts. And it supports a client-server model. So another binder located, same machine, different machine, even another microcontroller, can actually export as a server the sets of APIs it's hosting. And that's what we use here to mount a remote, somehow mount. It's a, you could say it's some kind of a WebSocket mount that we're using, if I were to simplify things. And that way we can access the cloud side on the edge. And this way, the service is able to run and read from one end the local Redis store and write on the remote side this way. And that is done with the knowledge of priorities and connectivity. We get, the framework supports events. So we get events when the bandwidth changes. We get events when the link goes down or when it goes back up. And so we can adapt our replication this way. And some of you might actually wonder why you're not using the normal Redis replication mechanism, which comes as standard as part of Redis. And that's exactly for that reason, because with the way we're doing it, we can select what to replicate, when to replicate, and adapt that based on the link quality and the bandwidth here. In the next slide, now we arrived on the cloud side of things here. And I wanted to take a minute to actually detail what we are doing here. Right now, the data is written on another Redis cache or data store. We have, again, a plugin system, so we can extend that and write into other things, like other type of databases, or also use different type of transports. Like we could talk to an MQTT broker, use CoAP to discuss with other entities once we are on the cloud side of things. You can control, this way we can control what we do. We can jump on the cloud onto an on-prem or private cloud, or we could go directly to like Azure, Google, OVH, or AWS. Deployment-wise, and it's containerized. Technically wise, it's containerized. Right now, we are using LXD as the container engine because it's easy to deploy also on individual developer machines. In the links I'll put at the end, you can try it for yourself. You just need a Linux laptop with LXD, but it's very easy to. We use Packer to build our containers, and since it supports multiple container formats, we're in the process of moving that to things like Docker or OCI images, so that we can run workloads over orchestrators like Kubernetes. That's it for the cloud side of things. Now I wanted to highlight a bit more details on the security aspect, because we've seen that having security on the link is very important. I did not mention, but the framework already supports encryption through TLS. So we already have that level of security here. We can couple that with another VPN on the cloud if needed as well. But that does not allow to do what I explained earlier, which is selectively give access to different people at different time for the data, be they shipyard, ship owner, charterer, or marine mechanic if they need to do maintenance. We need to be able to finally separate that kind of access. And so we developed another component, which we call the OIDC Secure Gateway, because it talks and interfaces with OpenID Connect's identity providers. And what it does, and we'll see a diagram in the following slide, is that it protects the WebSocket endpoints that the binder itself actually provided. And so this way, we can extend the permission model that exists in the application framework and gate that with identity and security things from providers. So let me show you how this basically look like here. On the right, you have the part of the diagram which I already explained earlier, which is the cloud side. And on the left, it's the new part, and I'm going to talk about that in a second. If we go over how it actually works, you've seen at the top the WebSocket endpoint, and so an access would be done there. And how this works is when an access is done, the secure gateway would trap on the access and look at whether the route, that is a REST route, right? Like say /data or /admin, what kind of permissions are defined to be able to access that kind of data. And so depending on the configuration, it will go over and connect to an external identity provider, an IDP in the OpenID Connect sense, and get the security attributes it provides and match that with a local standard configuration that is in a local identity store. And so this way, we're able to finally select what each user might be able to do. And that check is done against two main things. I mentioned the local database, which is one thing. That database would also define a level of assurance, which is the trust you might have for a given identity provider. Say from 0, which means it's basically public, to 6, which is the highest, most critical data, and map that to the social identity provider security attribute. And this way, we can model a complex scenario like, as you can see at the bottom of the schema, the need to grant access, the need to have another authentication factor to access the most critical routes information-wise. Like the technician would need an NFC tag or a fob that they would need to present when they enter part of the ship, say the engine room, for instance, and we're able to model that in that regard. This is a part we're still validating at the moment, so I'm not going to show it to you in action, but I wanted to give you just an insight of how this works on the synchronization part of it, the cloud publication binding. And so here you can see a small video. I've started multiple terminals. On the left is the edge, on the right is the cloud. The top terminal is the Redis binding, actually integrating and having data being inserted from the sensors. The center terminal is the cloud publication binding itself, which is replicating the data from one end to the other. The bottom terminal is the control terminal. And the one on the right, which you see actually updates every 2 seconds, is the cloud side of things. And so every 2 seconds, it will get updates from the data over, in this case, over the satellite collection, managing the bandwidth link from the sensor data. And this is how we are doing it, to pull the sensor data from one end, from the edge, to the other end, which is the cloud side of things. With that being said, we're nearing the end of our talk. I wanted to make a small recap of where we are right now and what we said. We've seen at the beginning that there is a very strong need for connectivity on a modern marine vessel, right? And that this connectivity is often very unreliable or choppy. The sensors on the boat itself can generate a massive amount of data. That's also something that needs to be taken into account. So there is a need, as I mentioned, to scale. Cybersecurity is critical, and that applies to all parts of the infrastructure, both in vessel, at port, and also on the cloud infrastructure here. And through the previous slides, I wanted to show you what we did, especially for the SENATIC project, for securing that end-to-end funnel between the edge and the cloud in terms of connectivity. We do that through the application framework, which originally we developed for the automotive grade Linux project, and which we extended with new parts, OpenID Connect being one, the cloud publication binding being the other. And I did not mention that here, but we also upgraded, now we are at version 4, so that the framework, if you remember, I mentioned how it abstracts location, but also communication for each application. Originally, that communication was based on JSON, but when the number of sensors would rise, or we're talking thousands of sensors, or the frequency of upload would be very high too, we'd get performance bottleneck. So the latest version, which is V4, version 4, actually allows to use any kind of binary data to talk between applications, like be it CBOR, flat buffer, or other type of more compact formats than JSON, and avoid the communication between, to, and from JSON in between the applications. And that's the implementation we use in the SENATIC project here. Now, if you're interested in actually checking, we do develop out in the open, so everything is available. I've put down links for the cloud publication binding here, as well as the documentation. As I said, we're doing the final validation for the secure gate binding and component. So this source will land, we're targeting right now around the summer. It will be available on the same repositories again. We also, if you want to play more with the first with the binding themselves, but also with redpesk, the operating systems, we have ready-to-use packages as well, and you can use that. The link is here. And of course, if you want to help or contribute, you can reach the community, which we've built on 2 channels with redpesk Core and redpesk Marine on Element or Riot. if you're using it. It's another slide with link here, redpesk itself, as I mentioned, IoT.bzh. We have some of our publications which we've put here. And finally here, I've put down some links on the various documents that you might be interested in terms of cybersecurity in the marine context. And the one at the bottom, which I'm sorry, unfortunately, we don't see very well, which is around the application framework itself. If you want to dive more into that particular aspect, José Bolo has made some very interesting presentation. One of the links is here, which is a deep dive into the inner workings of the application framework, both on the communication side of things, as well as the security model that's behind it. So that's it for this talk here. Thank you very much for attending it, despite the small technical issues we've been having. I'm glad this was eventually solved. And if you have any questions, I'll be available to answer them. So at this point, let me stop the presentation and talk and get back over to the live feed, and hopefully you guys can see me well. Perfect.